The chip inside your phone and inside the servers running AI is no longer a flat sheet of silicon. It's a building. That quiet change is fueling one of the biggest supply crises in tech. Let's go beneath the screen. Welcome to the Tech Beneath. For 60 years, progress meant one thing: shrink the transistors, pack more onto a flat chip. That was Moore's law. It worked because smaller transistors stayed cool too. Then, in the mid-2000s, that rule broke. They leaked power and ran hot. Moore's law didn't die. It got brutally expensive. And a deeper problem appeared. Not how fast you compute, but how fast you feed it data. This is the memory wall, and generative AI, moving billions of parameters every second, slams straight into it. When a city runs out of horizontal space, it stops sprawling and builds up. Silicon just did the same. First move: stop making one giant chip. Break it into smaller specialized pieces, chiplets, already inside AMD and Intel processors. Then place those chiplets side by side on a dense silicon interposer. TSMC calls it CoWoS, Intel calls it EMIB. Then comes true 3D, stacking dies directly on top of each other, connected by vertical channels. Those channels are TSVs. Think of them as tiny elevators moving data between the floors of a silicon tower. The newer method, hybrid bonding, welds copper to copper directly. The chip stopped being a page. It became a vertical city of silicon. This isn't theory. AMD's 3D V-cache stacks an extra block of fast cache memory right on top of the compute die. More cache means fewer trips to slow memory. And on Ryzen X3D chips, that becomes real, measurable frames per second. One gamer, zero interest in the physics. And yet, the stacked chip just made their game smoother. Now the biggest player in AI hardware, HBM. Memory that stopped lying flat and stacked into a tall tower of DRAM layers. Those layers connect through the same vertical elevators, and the stack sits right beside the processor, feeding it at enormous speed. Every high-end AI accelerator, NVIDIA, AMD, Google, depends on HBM. It's the industry's most direct answer to the memory wall. Bring data physically closer, and both latency and energy drop. Without HBM, the modern AI boom simply would not run. In June 2026, IBM pushed the idea to its extreme, down to the transistors, an architecture they call nanostack. Instead of stacking chips, it stacks the transistors, around 100 billion of them on an area the size of a fingernail. IBM claims 50% more performance and 70% better efficiency than the 2 nanometer node, but commercialization is roughly 5 years away. And IBM's own 2 nanometer node, promised in 2021, arrived late. So treat nanostack as a research milestone, not a product yet. Building upwards solves one problem and creates several. The worst is heat. Every stacked layer traps the heat of the ones around it. Then there's yield. One defect in one layer can ruin the entire stack, and buried flaws are often impossible to repair. Advanced packaging is now a bottleneck. TSMC's CoWoS is booked out over a year, and HBM shortages may last until 2030. And nearly all of it comes from a handful of factories in Taiwan and South Korea. One disruption slows the whole world down. So what does this mean for you? Better battery and speed in top devices, but advanced packaging is costly, so prices stay high. And when an AI service feels slow or pricey, this shortage is often why. The digital world feels weightless, but rests on physical silicon. Chips didn't just get smaller, they started growing up, floor by floor. That's the tech beneath. You know what to do.